Okay, here are the notes for momentum part 2. Again, the big idea for momentum is conserved for all collisions as long as external forces don't interfere. Alright, conservation of momentum works a lot like when we talked about conservation of energy. Whatever energy you started with will equal the energy you end with. The same thing happens with momentum. Whatever momentum you start with will equal the momentum you end with. So the law of conservation of momentum states that in the absence of an external force, the momentum of a system remains unchanged. The force or impulse that changes momentum must be exerted on the object by something outside the object. Molecular forces within a basketball have no effect on the momentum of the basketball. A push against the dashboard from inside the dashboard inside the car does not affect the momentum of the car. These are internal forces. They come in balanced pairs that cancel within the object. So if you're riding in your car and you push on the dashboard, that does not make you go faster because you're part of the car basically from being inside. The momentum before firing is 0. After firing, the net momentum is still 0 because the momentum of the cannon is equal and opposite to the momentum of the cannonball. The force on the cannonball inside the cannon barrel is equal and opposite to the force causing the cannon to recoil. The action and reaction forces are internal to the system, so they don't change the momentum of the cannonball system. Before the firing, the momentum is 0. After the firing, the net momentum is still 0. No momentum is neither lost nor gained. This is like Newton's third law. Momentum has both direction and magnitude, so it's still a vector. The cannonball gains momentum, and the recoiling cannon gains momentum in the opposite direction. The cannonball system gains none. The momenta of the cannonball and the cannon are equal in magnitude and opposite in direction. No net force acts on the system, so there's no net impulse or in the system, and there is no net change in the momentum because everything was internal. In every case, the momentum of a system cannot change unless it is acted on by external forces. When any quantity in physics does not change, we say it is conserved. So conserved is a key word here for us, meaning unchanged. The law of conservation of momentum describes the momentum of a system. That's a whole system. If a system undergoes changes wherein all forces are internal, the net momentum of the system before and after is the same. Examples: atomic nuclei undergoing radioactive decay, cars colliding, and stars exploding. All of these are internal. Newton's second law states that if no net force is exerted on a system, no acceleration occurs. Does it follow that no change in momentum occurs? Yes, because no acceleration means that no change occurs in velocity or in momentum. Mass times velocity, which is our momentum. Another line of reasoning is simple, that no net force means there's no net impulse and there's no change in momentum. So, what does the law of conservation of momentum state? It's what we've talked about these first several slides. Alright, now on to collisions. Whenever objects collide in the absence of external forces, the net momentum of the objects before the collision equals the net momentum of the objects after the collision. Okay, we've talked about this in class. The collisions of objects clearly shows the conservation of momentum. The net momentum before the collision equals the net momentum after the collision. This is where the collision occurs, right at the equal sign, and we've done problems like this. So, elastic collisions, things that hit and bounce off one another. When a moving billiard ball collides head-on with a ball at rest, the first ball comes to rest and the second ball moves away with a velocity equal to the initial velocity of the first ball. Momentum is transferred from the first ball to the second ball. When objects collide without being permanently deformed and without generating heat, the collision is an elastic collision. Colliding objects bounce perfectly in perfect elastic collisions. The sum of the momentum vectors is the same before and after the collision. Here's an example. A moving ball strikes a ball at rest. So before the collision, this ball is moving to the right. This ball is standing still. Here's our equal sign where the collision takes place. You can think of that as the plus, and that is the plus. If we're thinking about our formulas, there's the collision. After, this one's standing still now, and now this one's moving at the same velocity that this one was over here. Now look at a different way. They're heading opposite directions. So one of these has to be negative. I would normally say that this is the negative direction. We have this plus this equals, here's our collision, gives us, now they're going opposite directions. Now this one's going in the negative direction. And the third example, you see the vectors drawn here. This is a long arrow and this is a short arrow. Oops, that was a very poorly drawn arrow, meaning that the ball here is going faster than the ball here. Once they hit, here's your equal sign again, transfers, this is now the small arrow, and this is the longer arrow, so it transferred the momentum into that ball. A collision in which the colliding objects become distorted and generate heat during the collision is an inelastic collision. Momentum conserved holds true even in elastic collisions. Whenever colliding objects become tangled or coupled together, a total inelastic collision occurs. In an inelastic collision between two freight cars, the momentum of the freight cars on the left is shared with the freight car on the right. We have one that's traveling at 4 meters per second, and we have one that's at 0. They hit, here's our equal sign, equals. Afterwards, our mass now has doubled, so our velocity now is going that direction in 2 because our mass has increased, so our velocity has to go down because mass and velocity have an indirect relationship. The freight cars are equal of mass m, and one car moves at 4 meters per second towards the other car that is at rest. Net momentum before the collision equals the net momentum after the collision. If you look at what happens here, you have m at 4 meters per second plus 0 equals 2 after. So you have twice as much mass as moving after the collision, so the velocity after must be 1/2 of it before. Because you had 4 meters per second at 1 m, afterwards you have 2 m going 2 meters per second. The initial momentum is shared by both cars. Without loss or gain, momentum is conserved. External forces are usually negligible during the collision, so the net momentum does not change during the collision. External forces may have an effect after the collision. Billiard balls encounter friction with the table and the air. After a collision of two trucks, the combined wreck slides along the pavement and friction decreases its momentum. Two space vehicles docking in orbit have the same net force just before and after the contact, since there is no air resistance to space. The combined momentum is then changed only by gravity. Perfectly elastic collisions are not common in the everyday world. Drop a ball and after it bounces from the floor, both the ball and the floor are a bit warmer. At the microscopic level, however, perfectly elastic collisions are commonplace. For example, electrically charged particles bounce off one another without generating heat. They don't even touch in the classic sense of the word. An air track nicely demonstrates conservation of momentum. Many small air jets provide nearly frictionless cushion of air for the gliders to slide on. One glider is loaded so it has 3 times the mass of another glider. The loaded glider is initially at rest. The unloaded glider collides with the loaded glider and 2 gliders stick together. Describe the motion of the gliders after the collision. The mass of the stuck together gliders is 4 times that of the unloaded glider. The velocity of the stuck together gliders is 1/4 of the unloaded glider's velocity before the collision. This velocity is in the same direction as before, since the direction as well as the amount of momentum is conserved. Do the math. Consider a 6-kilogram fish that swims towards and swallows a 2-kilogram fish that is at rest. If the larger fish swims at 1 meters per second, what is its velocity immediately after the lunch? Momentum is conserved. And I can't read this because my fish are in the way. Constant at lunch until, if so brief for an interval, water resistance does not have time to change it. So if you have a 6-kilogram fish and it's traveling at 1 meter per second, that's going to equal, once it eats the other fish, you're going to now have 8 kilograms. And we're going to want to know what's the velocity afterwards. So you have 6 times 1 is 6 equals 8 kilogram V. So I divide by 8, so 6 divided by 8 gives me a fraction. So V equals 6/8. And I guess if I waited to get to this slide, it shows you the 6/8 that I got here, or 3/4. of the meters per second. Suppose the small fish is not at rest but is swimming towards the large fish at 2 meters per second. If we consider the direction of the large fish is positive, then the small fish has to be going -2. We've talked about this in class. You have to be wary of negative directions. So looking at the math this way, we have our 6 kilogram fish that's going 1 meter per second in the positive direction. We have a 2 kilogram fish that's going -2 meters per second in the negative direction. The bigger fish eats the little fish. How fast are they going afterwards? So 6 plus -4 equals 8 kilograms V. This is what we're looking for. So you end up with 1/4, or 0.25 meters per second. If the small fish were swimming at -3 meters per second, then both fish would have equal and opposite momenta. 0 momentum before launch would equal 0 momentum after launch, and both fish would come to a halt. Suppose the small fish swims at -4 meters per second. The minus sign tells you that after lunch, the two fish system moves in the opposite direction to the large fish. So you have the 6 kilogram fish going 1 meter per second, and the 2 kilogram fish is going -4 meters per second. That should be equals. Right there. Equals this. They eat, and how fast are they going afterwards? You see you get -2 over 8, -1/4. So it's saying that they are now going the negative direction at -0.25 meters per second. How does conservation of momentum apply to collisions? Okay, momentum vectors. The vector sum of the momenta is the same before and after a collision. Momentum is conserved even when interacting objects don't move along the same straight line. To analyze momentum in any direction, we use the vector techniques we've previously learned. We'll look at a momentum conservation involving angles by considering 3 examples. So look, we have momentum of car A, momentum of car B, momentum of car A and B. So we have one going one way. So momentum of A is just going this direction. Momentum of B is going this direction. So A and B together is going to be the hypotenuse. Something seems like it did not copy over. The momentum of car A is directed due east, and the momentum of car B is due north, meaning that you're going to get that being your resultant vector. When the firecracker bursts, the vector sum of the momentum of its fragments add up to the firecracker's momentum just before. So you have stuff going off this direction, stuff going off this direction, and stuff going off this direction. A falling firecracker explodes into 2 pieces. The momenta of the fragments combined by vector rules to equal the original momentum of the falling firecracker. Momentum is conserved for the high-speed elementary particles as shown by the tracks they leave in bubble chamber. So you can see high-speed light as it travels through here also has vectors that it travels in. Subatomic particles make tracks in a bubble chamber. The mass of these particles can be computed by applying both the conservation of momentum and conservation of energy laws. The conservation laws are extremely useful to experiments in the atomic and subatomic realms. What is true about the vector sum of momenta in a collision? We just talked about it.